Hello everyone, welcome to the second part of the lecture on Newton's method. In the previous lecture, the general algebraic formula for the iteration was derived, which is xk sub k plus 1 equal to xk minus ratio of the function and its first derivative. Here k is the iteration number. Now the above formula is valid if and only if the first derivative is not 0 for each k, for each iteration value. So that is the condition, otherwise this formula, the iteration formula, will blow out. It was shown in this method that this is a super linear method. We showed it in the previous slide. So here is some typo here. Let me correct it. It will be super linear, and hence the iteration converts to a fixed point very fast if we start very close to the x star. That means starting point x0 will be very close to x star. So let's find the solution of the function f of x equal to 1 over x minus a, where a is some positive number. Note that this function actually shifted from the inverse function, which meaning that that is our x, that is our y, that is a y equal to 1 over x. That is the graph of this function. We shift this graph downward by amount a, then we get this new graph. Clearly, if we shift it down, it will cross the x-axis at x equal to 1 over a. Clearly, the graph of f of x intersects the x-axis at x equal to 1 over a. Therefore, x star is 1 over a, and it is the root of the function f of x. Now, we sketch this graph in the next slide with a equal to 0.5. So to just give an idea what it look like and what we're going to do in the next. There is x, here is f of x. Okay, that is our, here is 1, so 1, 2, here, 1 here. So it will cross the graph at this point, so it will go this way. There is the graph look like. Okay, it is crossing the x-axis at this point. That is our x star. So idea is the following: we need to choose any point. That means x naught must be between 0 and 2. Why is that? Because if you choose the point here, that means from here up to here, that is the this interval, then you see the tangent will always intersect x-axis. There is no way we can avoid that one, so it will be converging. But if you choose x naught is too large, further down the x-axis here, then you can see tangent, that means it will asymptotically become flat, so it will diverge instead of converging, so we will not get the desired result. So this is the sketch of the graph of f of x at a equal to 0.5. Applying Newton's method, the iteration formula is here. So we now put the function and this first derivative with a equal to 0.5, and you rearrange. That is our iteration formula. Again, there is a one typo here. This should be 2 times x sub k. That is our correct iteration formula here, including 2. Now using this iteration formula, and then start the iteration with x0 equal to 1, and then make a table with a 4-column table here for first, second, third, and fourth column. Okay, now here x is equal to 2, so that is the second column gives the error term, deviation from the actual root, and third column is the familiar ratio, which is the according to converging mapping theorem, it will get smaller and smaller but non-zero. I can see very clearly after 6 iteration the error here is less than machine F cycle. That's why it is super linear. And fourth column, there is the new column here, will explain the meaning of this term later, but we write for sake of calculation that we can refer to in the later slide. It is a uh, ratio of x2 minus x minus x sub k divided by 2 minus x sub k minus 1 whole square. So in the limiting string, this is look like a second derivative. Third column look like a first derivative, and this fourth column look like a second derivative. It is not necessarily just a idea. Okay. The important point is that the values are constant. That is the important. Okay. Now the fourth column is new. Of course, it is related to the order of convergence. What it means is the following. To understand this, its significance, we need to go back and understand or recall actually the meaning of convergence rate, lambda, and the differential behavior of differentiable function. Note that for any function h of x, the first derivative h prime of x is 0, means that the delta h goes to 0 faster than the delta x goes to 0. The numerator, this is the numerator and that is the denominator. Since the numerator goes to 0 faster, the ratio also goes to 0. That is the superlinear case. But for linear case, actually, which is for lambda is less than 1 but greater than 0, these two ratios or the two terms, delta g and delta x, changes at the same rate asymptotically. That's why the ratio becomes fixed but non-zero fixed. The question is the following, that is it possible somehow to define or redefine lambda such that the ratio will become or not zero finite number like a linear case. Okay, so that is the idea and that is the question. The answer is yes, we can do. That is known as the order of convergence. Recall the definition of the convergence or rate or the ratio. So there is another typo here, so there will be no n here, ratio. There is the definition of lambda, the convergence. Right hand side is the first derivative of g, and that gives the, if the value is 0, it is superlinear, is the fraction, less than 1, greater than 0, it's a linear. Now in analogy with this one, we define or redefine the convergence of order alpha as this equation, lambda equal to g prime at x star, but look at the limit here first. Limit x goes to x star, the numerator is same but denominator xk minus x star whole to the power alpha. That is the index numerical value alpha. The alpha is known as the order of the convergence. Compare these two first derivative formula and here is this one. So for if alpha is 2, we call it a quadratic order 2 or quadratic convergence. That is the fourth column in the previous table. That's what we saw here. So clearly for linear convergence alpha equal to 1. So, and it should be noted that the alpha does not have to be an integer. Okay? It could be a fraction, it could be any other number. Okay? There is one more fact we need to be very careful. So since Newton method required that f prime or first derivative cannot be 0, we need to take extra precaution to choose the initial point x0. Otherwise, we might run into an infinite loop. The reason is the following: because if we deal with a graph that has a higher power, because it is non-linear, it must have a higher power of the variable, then it also has a turning point. Okay, and at the turning point, the slope is 0. So if this turning point fall into the two iteration point, then we'll be trouble because on one side it will be positive, other side will be negative slope. So what do you mean by that? Let's understand. While computing iteration, let's remember we compute this sequence. You start from x0, that's the initial point, and then compute x1 first iteration, then x2, and then xk plus 1 uh, the until the error becomes 0. We continue the computation. Now we need to make sure that turning point of f of x doesn't fall in between any two iteration points, because in that case we'll have a problem in the following sense, that if the slope at xk and slope at xk plus 1 will have a two different sign, because the turning point is in between. One will be positive slope, one will be negative slope. So if you continue the iteration, actually they will go back and forth between these two, positive slope to negative slope to positive slope. So we might fall into an infinite loop. That's the danger here. So as for example, to see this infinite loop, let's consider this cubic polynomial x cube minus 2x plus 2. The graph is shown in the next slide. Let's draw it here again. Not again, first time actually. Here is the graph. I'm sketching it, so let's see if I can do it correctly. Okay, so here is somewhere is roughly it is 2 here, and we have a somewhere 1 here, sorry, 1 here, 2 here, and so on. Okay, so this will be -1, and here is some -2. So it is not a scale graph. Okay, so definitely this is our root x star. Okay, now look at very carefully here. If I choose x naught, say here, as for example, okay, then by definition, remember that is our turning point here. There is a turning point. If you draw the slope here, look at here, it is a, that is our x k plus 1. The turning point is in between these 2 points. That is our xk, that is our xk plus 1, in between. So according to Newton's method, we have to draw a tangent here, and but this one goes here. Okay, but now that is a point here. It goes again back here, and then come here, come back here. So we are getting stuck in this loop here, going back and forth, back and forth. That is infinite loop. That is the problem, to have a turning point in between the iteration points. We have to avoid this one. That is the idea here. That is a precaution. So clearly x 0 equals 0 or 0 minus 0.5 lead to the infinite. So I give you two examples. One that is here, that is here. If you can check by calculation, that will got into a trouble. Okay. So to find the correct value of x0, we need to find the turning points. These are, so for this current given example, our turning point are plus minus root over 2 over 3. So we just solve this quadratic formula. Okay, one is a positive, one is a negative. So the negative one, that we need to take that one, and the positive one is really the turning point. Here clearly x0 need to be chosen less than minus 2/3, which is minus 0.8, because this is close to the x star. Otherwise the iteration will lead to an infinite loop. As for example, if we choose x0 equals 0, the iteration gives x1 equal to 0 minus the ratio of these two values, and if we just compute using the given values, they'll find is equal to 1. And then we compute x2, which is by the same formula, iteration formula, then x2 becomes 0. So that means we're going back and forth between 0 and 1, 0 and 1. So it is infinite loop. This happens because the turning point, which is plus 0.81649, is between 0 and 1. At 0, it is the slope is negative. At 1, slope is positive. Okay, and the turning point is in between. Similarly, x equal to minus 0.5 also have the same kind of problem. Hence, x equal to minus 1 would be the correct choice to start the iteration. It will be correct choice because it is less than this value. Okay, because our turning point is minus 0.816, so our minus 1, the point iteration point is less than that one, so it is in between the actual root and the turning point. So it is that when you draw the tangent, it will not cross the turning point, so we don't fall into an infinite loop. So it is more close to the fixed points, and it will after a sufficient iteration number, it will converge to a minus 1.7692. So that is our actual root value. This is also consistent with the statement that if x0 is close to x star, then the iteration will converge to the nearest fixed point. You already learned from the contraction mapping theorem. The example clearly indicates that the choice of x0 is still requires more attention. Not all values of x0 lead to converging iteration, even though it may be relatively close to the fixed point. The turning point must not fall in between the iterated point. That is the important point. So in the next lecture, we will learn how to make the Newton's method even faster, even though it is already superlinear. So until then, take care of yourself, stay safe, be safe. Thank you very much.